Here begins the essay. The year 1798 marks a pivotal moment in the annals of mathematical physics with Joseph Fourier's seminal treatise, The Analytical Theory of Heat. This essay undertakes a comprehensive and critical examination of this groundbreaking work, dissecting its core arguments, scrutinizing its methodology, and assessing the validity of its claims. Section by section, we delve into the meticulous detail with which Fourier lays out his mathematical framework, assessing its lasting impact on the understanding and representation of heat phenomena. We aim to extract the essence of Fourier's contributions, avoiding a mere rehearsal of established knowledge, and instead offering a sustained, in-depth analysis geared toward a knowledgeable audience. Section 1: Preliminary observations concerning the nature of heat. Fourier commences by establishing fundamental principles concerning the nature of heat, rejecting unsubstantiated hypotheses prevalent at the time. He asserts that heat, regardless of its ultimate nature, behaves according to discernible laws that can be expressed mathematically. He posits that the communication of heat between bodies occurs based on a difference in temperature, a seemingly simple concept yet ripe with implications for mathematical modeling. This section's claim that such communication is governed by temperature differences alone is bold. He acknowledges the potential influence of other factors, then prevalent in scientific discussion, such as the specific nature of the material involved, yet he consciously sets them aside for the sake of simplification. He argues, implicitly, that such factors are secondary in their effect. We find merit in this approach. By isolating temperature differences, Fourier is able to build a robust mathematical framework applicable to a wide range of scenarios, laying the groundwork for subsequent and more complex Section 2: On the uniform movement of heat in an infinite solid. Here, Fourier analyzes the propagation of heat within an infinite solid where the temperature at each point depends solely on the distance from the origin. The central claim is that under specific boundary conditions, the temperature distribution will evolve according to a diffusion-like equation. The derivation of the heat equation in one spatial dimension, specifically focusing on the linear flow of heat, is a landmark achievement. Fourier derives the partial differential equation describing this phenomenon, which states that the rate of change of temperature with respect to time is proportional to the second derivative of temperature with respect to position. This proportionality constant, the thermal diffusivity, combined properties of the material such as its thermal conductivity, density, and specific heat. The specific solution Fourier offers assumes a steady-state condition. This is an important limitation and points to the early stage of his analysis. While the steady-state solution provides valuable insight into heat distribution, it fails to capture the dynamic evolution of temperature over time under more general circumstances. We observe a degree of mathematical elegance in the assumptions that lead to the solution. However, it is in the later sections, as he relaxes these assumptions, that the true power of his analytical method becomes. Section 3: On the movement of heat in a ring. Moving from the infinite solid to a more constrained geometry, Fourier considers the flow of heat within a circular ring. This restriction allows him to explore the impact of boundary conditions and periodicity on the temperature distribution. He introduces the concept of periodicity, a cornerstone of Fourier analysis, which is, perhaps, the most lasting consequence of this work. He posits that any arbitrary function describing the initial temperature distribution along the ring can be represented as an infinite sum of sines and cosines. This is the origin of the Fourier series. He derives the solution to the heat equation on the ring subject to specific initial conditions. He then makes a crucial leap: the assertion that any function, even one with seemingly arbitrary shape, can be decomposed into these sinusoidal components. This claim, revolutionary for its time, is the linchpin of Fourier analysis. While the underlying assumptions concerning convergence and differentiability were not completely rigorous, the practical applications of this decomposition proved to be undeniably powerful. Section 4: General equations of the movement of heat in solid bodies. Fourier broadens his analysis to 3 dimensions, formulating the general heat equation that governs the flow of heat in any solid body. Here, the temperature becomes a function of 3 spatial coordinates and time, and the heat equation involves partial derivatives with respect to all these variables. He states that the equation, now expressed in its full generality, captures the essence of heat propagation in any solid object, irrespective of its shape or internal structure. The derivation of this generalized equation is a testament to Fourier's mathematical prowess. He provides a methodology for calculating the temperature distribution within a body given its initial temperature and boundary conditions. The challenge, of course, lies in solving this equation for specific geometries and boundary constraints. Fourier attempts to illustrate the versatility of his equation, outlining methods to solve it in specific cases. The analysis is less rigorous than in the previous one-dimensional case. While the equations are correct, the methods Fourier proposes for obtaining general solutions are not universally applicable. The path to solving these equations is not necessarily straightforward. However, the significance of this section lies in its ambition. Fourier lays the foundation for the analysis of heat transfer in complex systems. Section 5 on the propagation of heat in a solid sphere. Fourier now explicitly solves the heat equation for a solid sphere. He applies the general solutions derived in Section 4 to this specific geometry. The geometry of the sphere introduces spherical coordinates, simplifying the angular dependence of the temperature distribution, enabling the separation of variables. He provides a detailed solution to the heat equation, expressing the temperature distribution as an infinite sum of spherical harmonics. In addition to the time-dependent component, this solution involves Bessel functions and Legendre polynomials, specialized functions which arise naturally in spherical systems. He demonstrates through explicit calculation how the temperature profile within the sphere evolves over time, given an initial temperature distribution. The complexity of the solution highlights the challenges involved in applying Fourier's general methodology to specific problems. While the mathematical formalism is correct, the practical computation of the temperature profile requires significant effort, even with the aid of modern computers. The solution, however, provides a clear illustration of the interplay between geometry, boundary conditions, and heat propagation. Section 6 on the propagation of heat in a solid cylinder. Shifting focus from spheres to cylinders, Fourier investigates the heat flow within a cylindrical domain. The cylindrical geometry allows for an exploration of axial symmetry and its impact on temperature distribution. He adapts the general heat equation to cylindrical coordinates, resulting in a modified equation that reflects the symmetry of the cylinder. He solves this equation using a method analogous to that employed for the sphere, separating variables and obtaining solutions in terms of Bessel functions. He presents solutions for various initial temperature distributions and boundary conditions, including cases where the cylinder is heated uniformly or subjected to a localized heat source. The solutions obtained are similar in structure to those for the sphere, reflecting the commonality of the mathematical approach. The analysis reinforces the idea that the fundamental principles of heat propagation remain the same, regardless of the specific geometry. Section 7, the general equation relative to the surface. Fourier shifts emphasis from heat distribution within a solid body to the interactions at its surface. He derives an equation that describes the balance of heat fluxes at the surface, taking into account radiation, convection, and conduction. Here, the surface is treated as a boundary where heat can be exchanged with the surrounding environment. The equation emphasizes that the net heat flux at the surface must be zero. Fourier introduces coefficients that characterize the rate of heat transfer by radiation and convection. Acknowledging the complexities involved in modeling these phenomena, the equation provides a framework for analyzing various scenarios, such as the falling of a heated object in air or the heating of a surface or sunlight. Section 8 application of these principles. Fourier provides concrete examples to illustrate the applicability of his theoretical framework. He shows how the heat equation, along with appropriate boundary conditions, can be used to predict the temperature distribution in various physical systems. He estimates the time required for an object to cool down to a certain temperature, or determines the temperature profile in a heated rod. He compares his theoretical predictions with experimental observations, demonstrating the accuracy of his model. The examples serve as a validation of Fourier's analytical methods. His approach demonstrates that the heat equation can be used to solve real-world problems, ranging from the design of heat exchangers to the prediction of temperature fluctuations in the atmosphere. Section 9. Further examination of the principles. Fourier revisits his principles, attempting to refine and clarify them. He addresses potential objections to his mathematical approach and discusses the limitations of his model. He acknowledges that the assumption of a homogeneous and isotropic material is an idealization. He concedes that real materials may exhibit variations in thermal conductivity and density. He discusses the impact of these variations on the accuracy of his results, suggesting that the heat equation remains a valuable tool, even in cases where the material properties are not perfectly uniform. His critical evaluation enhances the credibility of his work, demonstrating his awareness of the assumptions and limitations inherent in his model. He does not claim that his model is perfect, but he insists that it provides a valuable approximation of reality. Section 10. Historical digression. Fourier departs from the purely technical, providing a historical overview of the study of heat. He acknowledges the contributions of his predecessors, acknowledging the contributions made by scientists such as Newton, Laplace, and Biot. He traces the evolution of the understanding of heat from its early association with fire to its eventual recognition as a form of energy. He places his own work within this historical context, highlighting the novelty of his mathematical approach. This digression provides a broader perspective on Fourier's contribution. He is not merely presenting a set of equations, but rather contributing to an ongoing scientific endeavor. He emphasizes the importance of both theoretical and experimental investigations, noting that progress in the understanding of heat has often relied on the interplay between these two approaches. Section 11. On thermometric scales. Fourier examines the methods used to measure temperature. He discusses various types of thermometers and compares their advantages and disadvantages. He emphasizes the importance of having a standardized temperature scale, arguing that a reliable scale is essential for accurate scientific measurements. He analyzes the properties of various thermometric substances, such as mercury and alcohol, and discusses the factors that influence their accuracy. He acknowledges the challenges involved in establishing a truly universal temperature scale, given the limitations of existing thermometric technologies. The discussion of thermometric scales highlights the importance of precise measurements in the study of heat. Section 12. General considerations. Fourier concludes his treatise with a reflection on the broader implications of his work. He emphasizes the universality of the heat equation, expressing the belief that it applies to a wide range of physical phenomena, including those beyond the realm of heat transfer. He speculates on the potential applications of his analytical methods to other areas of science, such as fluid dynamics and electromagnetism. Fourier's concluding remarks reveal a vision of a unified science, where mathematical principles provide a common language for describing diverse natural phenomena. He sees mathematics as a tool for uncovering the hidden connections between seemingly unrelated fields. His work exemplifies this vision, demonstrating the power of mathematical analysis to illuminate the fundamental laws of nature. In conclusion, the analytical theory of heat represents a monumental achievement in mathematical physics. Fourier's rigorous analysis, combined with his bold claims regarding the applicability of Fourier's series, has had an enduring influence on science and engineering. While the work includes limitations, particularly in its initial assumptions and computational feasibility, its intellectual depth and far-reaching implications solidify its place as a cornerstone of modern scientific thought. The impact resonates through the development of signal processing, image analysis, data compression, and countless other technological advancements, all stemming from the profound insights contained within this groundbreaking treatise. The spirit of Fourier's work continues to inspire scientists and engineers, demonstrating the power of mathematical analysis to unlock the secrets of the natural world.